All right. Let's get going. We've got new month. New month. We don't have we don't have many classes left. I think we have our third exam 3 Fridays from now, I believe. It's a Friday right before Thanksgiving break. So start planning for that. And our final exam is Monday of finals week, 8 a.m. So again, mark that on your schedule. I think we have a quiz that's due. Is that right? And we also have the homework problems, right? Those were, I think that's due on Tuesday night. So that way, if you have questions and not sure how to do them, you could ask them today if you have any questions, or bring them to class on Wednesday. So estimating population sizes and so forth. We're not done with that because we're going to add additional equations that account for some of our regulatory factors. Yep.
Are you saying wasn't due till the Friday before the test? I thought it was a homework problem.
Overall, but I believe I set the 2 dates to try to get it done, because if you wait until the week of the test and you have no idea how to do it, then you're kind of at a loss. You're not going to learn how to do it. Not with these equations coming up. So yeah, I asked to have it done this week so that way we can answer the questions, because then I also have practice problems for the exam that I'll get posted, because those will all, I think they're already posted. They include our population growth. They also include, what did we do? Dispersion, variance mean ratios, coefficient of association, all of that's on this third exam. So we have more calculations, more equations on this third exam. All right. So this is where we left off. We talked about exponential growth. Exponential growth had some assumptions. What were the assumptions? Give me one assumption of exponential population growth. All right, so closed population, no migration happening. What else? Yeah, constant R. So R can't change through time. It has to remain constant. So when we predict our population, we get this real nice smooth curve. What else? Okay, no age or size structure. So all individuals, if they have an expected reproductive output or reproductive potential, they remain, I should say, reproductive output's a better term. It's the same reproductive potential, and that affects our R. That affects intrinsic rate of growth. What else? That's 3. Yep, no time lag. So we're measuring instantaneous change, a change immediately that happens. So they're going to mate and they're going to reproduce and produce those offspring, immediately. And then our last assumption. Yeah, no genetic structure. So our population has to be a real population. That entire population has to represent the deme, which would be our randomly mating population. All right, we can't have individual demes that end up leading to specific, genetic groups. You could say ecotypes, they're at least probably on their way towards becoming an ecotype at that point. We need them to be homogeneous. We need the R to be the same across individuals, across that population. And if these 5 assumptions are true, then we could model population growth using the exponential growth equation. But that usually isn't how things work, all right? Because we have other factors that influence our population, factors including competition for limiting resources. So as we increase our population size, we're actually increasing our competition for those limiting resources. It's going to be harder and harder and harder for every individual to get the same amount of nutrients, same amount of resources, and thus now we start to see changes in our intrinsic rate of growth. Now, what's going to cause the changes in our growth? It could be a change in the birth rates, it could be a change in the death rates, it could be a change in our migration rates, in immigration and emigration. All right? So what we have to recognize is that it's both biotic and abiotic factors that are going to influence our populations. They're going to regulate our populations. So that's what this graph was just kind of pointing out. It's how these various events will affect our mortality and reproductive rates. It doesn't have to affect both. They usually do. It could only be mortality or it could only be birth rates. All right, so biotic factors are normally broken down into factors that are considered top-down factors or bottom-up factors. And this is relating to, do we have predators regulating our population or do we have the food supply regulating our population? So this top-down, bottom-up fashion all relates to where we're at in our food chain or our food web. All right, so I know in the principles course, you've learned about a food chain. What's a food chain? Up there. It's a hierarchical pattern of energy transfer from our producers to our consumers. Right? We talk about, or you hear about a supply chain, in the news. Yeah, this is our food chain. Is how does that energy move through our system? Now, as it's presented, or how it has been presented to you, in elementary school up through high school, and possibly even in the principles course, is that you have this very nice linear pathway. All right, you've got your plants, they go to the herbivores, they go to the predators. All right, it's a very simplified view. In reality, it's probably more like a web, where you have your plant that could be consumed by multiple different herbivores, who could then be consumed by multiple different predators, and you've got this intricate web of all of the interactions. But it just doesn't change the fact that we can label various trophic levels on that web. So a trophic level is a set of species that feeds at a particular place in the food chain. So if we set it up, I'll do this on the board. If we set up a typical web, we can put everything that produces energy down here. So this might be plant 1, plant 2, plant 3. All right. So our producers are the ones that are taking the energy from the sun, converting it into organic molecules. Okay. So our trophic level, in this case, is our producers. And then our second trophic level are the consumers. So if we look at our energy transfer, we have these connections where these plants, as they produce energy, they're going to be feeding our consumer level. And this is our this is one of our trophic levels. And then we have our secondary consumers. This would be C5 and C6. C5, C6, that then eat our herbivores. So at each level, these represent our trophic levels. All right. And the entirety would represent, this would be our food web. All right. If we did a linear pathway, it would be more of a food chain. Now, our trophic levels can become a little bit more specific. So we have our primary producers. That are are these guys. And then our consumers can be broken down into our primary consumers, secondary consumers, tertiary consumers, and so on. All right, and what that just is saying is that where are we, what do we eat? So we've got our primary consumers are all eating our primary producers. Our secondary consumers are going to be consuming our primary consumers, but it doesn't just have to be our primary consumers. Some of those secondary consumers may also be able to feed on the primary producers. So like an omnivore, right? Could eat predators, could browse or graze, or forage. Now, our top-down or bottom-up fashion refers to where we're being regulated. So we'll pick C2, all right, consumer number 2 here. If they are regulated by the food supply, then they are being regulated in a bottom-up effect. Here we go. Bottom up. Why? It's because they're lower on this food web. The primary producers are regulating and governing population size at our primary consumer level. So our bottom up goes down here. It's having an effect above on the food web, trophic structure. If we are exhibiting or experiencing top-down control, we have our top level or higher levels of our food web that are regulating those that are below it. All right, they're regulating those that are below it. So as we have it here, if C2 is experiencing top-down control, then it's the predator, C5, because C5 consumes it, that's going to govern this population size. If it's experiencing bottom-up control, then it's going to be our plant 1, P1, producer 1. Now, this applies at our populations. That's what we're talking about. Right? But it's actually a lot more complicated than how we present it. All right? Because, let's look at C3. If we look at C3, maybe it's looking at bottom-up control because it's a food supply. But what if C2 is regulated by the predator up here? This C5 regulates C2. C2 consumes plant 2 or producer 2. So if these go down, this goes up, which now has an effect on C3. So as we're talking about this, we're focused at the population level, but we can also expand it to a community level, to where we have top-down control of the community diversity below it. Or we have bottom-up control that governs the diversity above the producer levels. All right, so just kind of as an FYI, remember, we're presenting this as a population control, but it can also happen at the community level. All right, and that's what this predators regulate herbivores and food supply and herbivores and so forth. That's what we've done. Our predators are up here. Our herbivores are down here as our primary consumers. Our food supply are the producers. They're regulating our herbivores and so forth. All right. So when we see this type of regulation, we often refer to it as density-dependent factors or density-dependent regulation. And it's because our processes that govern that population change based on how many individuals there are in that population. All right, so density-dependent factor is defined as a population process that changes with our population density. population process that changes with our population density. We're going to see this as either a change in our birth rates, change in the death rates, or both. Change in birth rates and change in death rates. All right, so this is a graph that kind of summarizes that. So we have our reproductive rates on the y-axis and against population density. All right, and that's going to represent our blue line. And then we have mortality rates against population density on our secondary axis. And that's going to be our orange line. So when you have density-dependent factors or density-dependent regulations, then what we should see is as we change our population density, our reproductive rates will change, or they can change. One of them has to change, either the reproduction or growth. So here, reproductive rates are pretty high when we have small population densities. But as we increase our density, as we go along this x-axis, our reproductive rates decline. Get to the point where when we have very high population densities, we have very low reproductive rates. All right, and I said it could be birth rates or death rates or both. Well, what about death rates? Well, typical situation is that our mortality rates are pretty low when we have low population densities. Basically, it's our standard mortality rates. It's whatever the natural mortality rate is. And then as we have these other regulatory factors come into play and our population density increases, now we start seeing increases of our death rates to where we have a higher mortality rate with a larger population size compared to smaller population sizes. All right, so we have bottom-up and top-down effects that we can model. All right, so let's talk about bottom-up. Get a piece of chalk. So he said bottom-up, density-dependent factors. So in a typical situation, we would see a population growth curve that looks something like this. We'll learn that this spot could represent a carrying capacity. All right. We'll assume this is food supply. What we could do is go through and supplement food supply to see if food supply is having an effect. And if it is, so this is without a supplement, then what we may see is our population grow up to a much, much larger population size. Now, we get this slowdown up here because as we start to increase our population, we're increasing competition. So the amount of food available per individual is going to start tapering off until we get to a point where our birth rates and our death rates match. So if we look at one of these graphs that I just put up, we've got our mortality. I'll do B for our birth rates and our population size. We may be right like this. Here's our births. Here's our deaths. Our crossing point right there represents our equilibrium. At this point now, our birth and death rates are equal. Now we change it as we increase the food, as we supplement it with food, we provide more resources available to our individuals, which now allows them to grow to a higher population size. And that's going to change. It's going to probably change our graph. So if we supplement our food, maybe our birth rates go up a little bit, and our death rates go down a little bit, which gives us to a higher population size, because we're looking at that crossing. What about predators? Well, predators can be the same, can do somewhat of the same thing. So we have our population size. So in general, food affects both birth rates and death rates, because you can account for more energy to contribute or to acquire and contribute to offspring, as well as less food available as we start to get to large population size. You start seeing more starvation and so forth. Predators, though, really don't have much of an effect on our birth rates. So in this case, maybe we have a predator. Or with multiple predators. All right, and then we go out and we do an experiment. We think our this population's top-down regulation. We exclude our predator. How can we exclude a predator? How could we exclude a predator? Let's come up with an example. Let's say we are looking at rabbit populations. And let's say our primary predator is coyotes. How do we go out, we measure population size, we look at regulations, and when the coyotes are present, that's what we look like. That's what our rabbit population looks like. How do we get to this? How do we exclude our predators? What can we do? What do you think? Yeah, you can shoot them. That's probably a decent way. How do we ensure that there's no other predators that come in? What else do we do? Fence it off, too. So yeah, you're right. We do, once we set up that fence, we need to make sure we exclude all the predators. So you will have to go out and shoot them or trap them and remove them. Do something to get them out of there, but that fence then helps to keep any of them from coming back into that population, because our predator population is also experiencing control. They're also in competition. So if we set off this big ranch and fence off the big ranch and get rid of them, hey, that's a prime habitat. Those other coyotes are looking through the fence and saying, I wish I lived there. Look at all those darn rabbits. All right, so yeah, just an idea. But we have our higher population size. Now, how does that affect? What is our graph here? So here's our death rates, here's our birth rates. Well, our birth rates probably are unchanged. But when we look at our death rates, here's our death rates. Now, once we remove our predators, we are reducing how many of them are being eaten by our predator. And now that causes our population to be able to reach a larger size. Because again, our equilibrium size happens when we cross these two lines. So we've got our bottom up and our top down regulation. This point represents our equilibrium, those points. Our equilibrium population size, and in some cases it could be our carrying capacity. We'll talk about that in a bit. All right. Any questions? So that gets us to our model. So with our population models, we recognize that populations don't grow to infinity. They are regulated. And when we actually look at populations, real populations, they tend to exhibit this type of curve, this S-shaped curve. This S-shaped curve is called a logistic curve. And it follows a logistic growth equation. All right, it's a logistic growth equation. Now, with our logistic growth equation, we could generate an equation that predicts a population size in a certain amount of time. But it's a pretty nasty equation. Easier equation to work with, and I think one that helps us better understand what's going on here, is our change in population size equation. Right, so we're not going to calculate population size at a certain amount of time. We'll estimate a change in population size. So our change in population size is modeled with this equation here. Our change in population size, dn over dt, it's going to be dependent on our intrinsic rate of growth, or instantaneous rate of growth, our population size, and K, where K is our carrying capacity. The carrying capacity is the number of individuals that can be supported by the resources available to the population. The number of individuals that can be supported by the resources available to the population. So just for semantics, if we go back to our graph here with our predators, this isn't really the carrying capacity. That's our carrying capacity. That's our carrying capacity. This is our equilibrium population size. So we didn't have predators in it. So what's regulating our population? Our food supply. Those resources determine our carrying capacity. If we go back to this graph, we added our food supplements, we've changed our resources. And now, that's our carrying capacity. We've altered our carrying capacity. Now you could argue and say, well, there's predators there. Shouldn't those be equilibrium population size? Yeah, but we'll assume that there are no predators for this case. Because the key point here is we're trying to separate carrying capacity from an equilibrium population size. Because the equilibrium population size is going to be affected by a lot of different things, whereas our carrying capacity is all about the resources. How many resources are there that can support a population? All right, so with our equation, we have our regular exponential growth. This R times N, we've seen that. All right, and in that type of population growth, we assumed that there were no regulatory factors. There was no density dependence. All right, so in our density dependence equation, which is this part, the K minus N over K, or it could be simplified to 1 minus N over K, we assumed that density dependent was 0. There was nothing. So that's how we got our dN over dt equals R times N. That's our exponential growth equation. But now we're going to factor in density dependence. And this density dependence part is talking about how close, it's trying to figure out how close are we to the carrying capacity. And then adjust from there. Then adjust from there. All right? So our population size starts out very low, and it looks like it is exponential growth. And then as we start adding individuals, we become less and less exponential, up to the point where instead of increasing and increasing more rapidly with each time point, now our increase starts to slow down until we get to a point where we flatline. where we basically stop growing. All right? So this k minus n over k term looks into that and says, as we are far away from the carrying capacity, as our n is far away, this term starts to become 1, or is close to 1. So it makes us look like we're exponential. But as we increase in size and get up to our carrying capacity, now we're at carrying capacity minus a population size that's right near that level. Well, a number by minus itself is 0. So it basically gets to the point where a change in population size is equal to 0. And that's what we see. That's what we see. So if we're below the carrying capacity, we get population growth. We grow up to the carrying capacity. If we're far away from it, we grow faster. We have a faster rate of growth. If we're close to it, we're going to have a slower rate of growth. All right? If we get to the carrying capacity, then we have 0 growth. We're basically there. But are we ever likely to get to that point? No. Because usually what happens is our population grows and then overshoots that carrying capacity. Can the equation handle that? Oh yeah. Because when our population size exceeds the carrying capacity, when this number is larger than k, now this term becomes negative. And once we have a negative number that we're multiplying values with, we get a negative answer, which indicates decline. So in a normal situation, typical situation, we have population growth, it overshoots the carrying capacity, and then regulatory factors kick in and bring the population back down to the carrying capacity. And then you can have something happen, let's say a weather event that caused an increase in a food supply, maybe. And we start but it's only a temporary increase. So now you get an increase in the population size again, but then as soon as it returns back to normal, now we go back to a negative population growth. Now, how likely is it that we go negative right to the carrying capacity? Not really common. We're going to undershoot it. And now once we undershoot, we're going to be less than our carrying capacity, and we start our growth again. All of the jaggedness is all about the uncertainty. There are other things that are happening that will affect our equations, will affect our population growth. Here, we're just talking about resources. That's what we're focused on. So, in summary, anytime we have an R greater than 0, all right, it indicates population growth unless we have regulatory factors. And then if we have density-dependent regulation, then it comes down to, 1, are we positive? Is R greater than 0? If yes, then let's look at N versus K. If our population size is very far away from that carrying capacity, we're going to experience growth. All right? Our growth is going to basically look like R times N. All right? And this is the reason why we measure R when our population size is small. This is the reason. If we're just below K, we still have positive. We're on the positive for our density dependence. So our dn over dt is still positive. If we're equal, if our population size is equal to k, then our change in population size is equal to 0. Our growth and decline, our birth and death rates are equal. If our population size is greater than the carrying capacity, then we switch to the negative. We're going to see growth, negative growth. And note, again, this is when our intrinsic rate of growth is greater than 0, and it usually is. Why is R almost always greater than 0? What happens if it's negative? What does that mean? Population decline, and if that's standard for the species, what's going to happen to our species? Yeah, it goes extinct. Yeah, so there are populations at certain times where R might be negative, but generally speaking, R is going to be positive for those species that still exist because we know that they survive and are around. All right, so in our graph, our logistic growth equations, we have a couple points to see. One is the carrying capacity. That carrying capacity is that flat line area. It's where we grow. It's whatever size we grow to. And that kind of sets up our, if we're below it, we grow. If we're above it, we decline. Half of the carrying capacity marks the inflection point on our graph. So we go from a concave up shape, all right, where we're curved going up, to a concave down shape. We're now curved going down. That point, half of our carrying capacity, is the point where we will see the maximum rate of growth. It's a maximum rate of growth. Now this graph is for our population size. So N versus T. Can we do the same for the dn over dt? Yeah, we can. So, and we see the same thing. So if we look at our change in population size, anytime we're above 0, we're going to have population growth. So if we start at this point on our line, see if I get, if we start there, at our very next time point, we're going to be up here, and we're going to keep growing because it's all positive. All right? And we're going to keep going all the way up to our peak, which represents the maximum rate of growth for our population. And that just happens at half of our carrying capacity. It's just defined. That's where it happens. And then once we pass it, we're still growing. So our population's still getting larger and larger and larger until it gets to this spot. That spot is our carrying capacity. That's our K. Mark that. That's our K. And then if we exceed our K, now we are at our negatives. So let's change the color. Go blue. So now, if we start there, our population's declining. And it'll keep moving us back to get to that carrying capacity. Why do we care about this point of maximum growth? Because that's where land managers try to maintain their population sizes. Because those managers are normally raising whatever they're doing, whatever they're raising, say deer herds, all right, or fish farms. Right? They're trying to make sure that their animals produce at the highest rate possible. All right? Now, in farm production, we tend to supplement things, be it even higher growth rates. But we know through time, and there's probably a class, like ag economics class, that talks about how do you maintain successful populations, how much should we supplement, and so forth. And it's all aimed at trying to maximize our productions, and we're looking for that point, that maximum rate of growth. So, just in summary, anytime we are above our carrying capacity, our population is going to be getting pushed back down. Anytime we are above our carrying capacity, or I'm sorry, not above, below our carrying capacity, we're going to be getting pushed up to our carrying capacity. That's how our logistic growth equations work. Questions? Can we model it? Can we estimate it? Yeah, we can. We need to know our R, we need to know carrying capacity, and we need to know the current population size. So here's an example problem. Yeast exhibit an intrinsic rate of growth of 0.25. We're going to grow them up in a vial, and that vial can hold 1 million yeast cells. So we have these 3 questions. What's the population growth rate when we inoculate the vial with 1,000 cells? What's our growth rate when we have 500,000 cells in the vial? And then what's the growth rate when we have 900,000 cells in the vial? So let's work through this first one. How do we do it? Put it up. We know our equation. Or maybe we don't know what we're going to use. Maybe we're reading this problem and have no idea where to start. We know it's a population growth equation. You know which ones to look at, but we don't know which one specifically to use. So we read through the problem, and we start writing down the information that's given to us in the problem. So the first thing we say R, intrinsic rate of growth, is 0.25. Okay, so that narrows it down to either the exponential growth equation or our logistic growth rate equation. Next part. A vial can hold 1 million yeast cells. Well, that's going to represent, so the vial is our resources. We're limited. They're limited in such a way that that vial can only support 1 million yeast cells. So that's our carrying capacity. 1 million yeast cells. That right there kind of gets us towards that logistic growth rate equation. And the only equation we have is dN over dt, which is R times N times our density-dependent growth equation, or part of our equation, which is that. So the question then asks, what is our change in growth, or our growth rate, when N is equal to 1,000? We inoculate our cells, or inoculate that vial with 1,000 cells. So we have R, that's given to us, that's the first part of our equation. We have K, what we didn't have is N until we actually read the question. So we inoculated with 1,000 cells, there's our N, what's our change in growth rate? So it's just substitution. We know the equation that we're going to use. So we just substitute our values in this part of the equation. 1 million minus 1,000 all over 1 million. And we pull out our calculator. So we got 0.25 times 1,000. That gives us 250 times this part. So we've got 1 million minus 1,000. My equal sign divided by a million. I get 0.999. That's our two sides. So our dN over dt, just multiply these values. I get 249.7. About 250. All right. We've got two other ones to practice. What I want you to do is work through these, have an answer for class on Wednesday, and then we'll kind of work through them and get some work up here. All right. We're doing the same thing. Key to these problems, to these word problems, write down the information that's given to you in those problems. And that should tell you what we need. I'm going to say the one exception is the doubling time. Remember that example problem where I gave you population size for the doubling time, right? Did the population size matter? No, doubling time, the only thing that mattered was that R. So maybe you get extra information. Now these problems, change in population size, population growth rates, you're going to have specific answers. All right, so quiz today. attendance quiz. Pull them out. It is done with Halloween. No more Halloween candy. But we're not close enough to Thanksgiving to do Thanksgiving dishes. So we're going to settle on Italian artists. Answered today is Michelangelo. I'll let you look up today in history. See where Michelangelo fits in. Michelangelo. And so Michelangelo was our quiz question. Parasites in the news. This popped up. Horrifying parasite masquerading as fish tongue found in Texan State Park. This was on the 29th of October. There it is. Look at that thing. Parasites are cool. Imagine that poor sap that caught it. Didn't realize what it was. It's, what kind of parasite is it? Who's had parasitology? You did. Did we talk about this? Someone present this? Symathoa. Yeah, it replaces the tongue. It's an ectoparasite, right? But probably about the only example we know where the parasite replaces an organ and actually still benefits that host because they've replaced it. Now the host is losing nutrients. All right, so there's our harm for the parasite. But I thought this was pretty cool. So parasitic isopods, crustaceans. That was in the news. All right, we're done. Lab this week. You can bring your laptop or tablet. We're doing life tables. All right, I did post data as an Excel document. Hopefully it can help simplify some of our calculations a bit. But it's going to be calculations. Working through calculations, making some figures, and then there's going to be a homework assignment too. So if you want to bring your laptop or your tablet to do it on your own instead of the lab computers, you are free to do so. All right, have a